Yeah, we're live, so I think let me just yeah, no, it's streaming. So let me present Amartya, who will tell us once more about extended reflection positivity for invertible topological quantum field theories. Please, Amartya, take it away.
Thanks, Grisha, for having me. So hope I'm audible properly. Okay, yeah, thanks for having me again. So this could be the last part of the talk. So here we'll talk about the main theorems of interest that we've been chasing since the beginning. So that is to find a homotopy type for the deformation classes of these continuous invertible reflection positive n-dimensional topological field theories with symmetry type HM. So that has been our goal from the beginning. So and that is something that we'll do. Right? So maybe okay. So here's the plan. Here's what I'll be talking about. So I'll just recollection, meaning I'll just define the way I define stability. So the main goal of this talk is to talk about stability, the way we investigate stability in these field theories. So that is first part of the goal, and the second part is to understand extended positivity. So this, to me, is the most important part. Like the way we can think about positivity as structure. Right? So there's a lot of geometry that comes into the picture, so that makes it easy first. And then we'll say the main theorem of interest, then maybe and we'll see that the goal that we've been chasing that will be a corollary of the main. And then we'll go through not the full details, but for I'd say around 70 to 80% of the details of the proof, because so the proof is like an argument that relies on other arguments which rely further on other arguments. It's kind of a chain, but we'll see. Right. So starting with recalling what I meant by stability, the way I had defined stable. So we've seen a lot of things in the first two talks. So let's see. Recall. An n-dimensional vertical topological field theory with domain. So these are matching to one spectrum which we saw is stable if it is the restriction theory. So cool. So now we will say that. So I won't prove these characterizations of stability actually, because of the purposes of the talk. So for that, the references of a Freed-Hopkins paper. But so the thing that we are doing is we are doing obstruction theory. So for investigating stability, so we have this sequence of German spectra that we saw before. So this is the sequence where we'll do obstruction theory on just don't need right. So first we begin. So as I had said, so we'll see why we work with these two cases. So the first case is dealing with discrete invertible topological field theories without reflection strength. So discrete invertible topological field theories with a reflection, without a reflection structure. I'm sorry if I said with. Okay, so here's the main theorem. Discrete vertical topological field theory is stable if and only if real x is 1. So, as I said, I will put the proof, but the reference remains the Freed-Hopkins paper. Also, the Gallipier's medicine paper, who's a which I shared with Risha, which I will probably posted as well. So then the subspace of this was our space of discrete invertible topology. So as I probably said, there's a lot of hefty invitations. I hope we go through that. With the so would satisfy this invitation right here. So that turns out to be homotopy equivalent to, so the way we define it, that should make sense. Right. So that was for discrete invertible topological field theories without a reflection structure. Now we turn our attention to continuous invertible topological field theories with a reflection structure. Again, so I'll just state the main theorem. An equatorial continuous invertible topological field. Stable if and only if type P. So okay, yes, okay. You have a digression in order to understand what this type P and type M means. So okay, a bit of a digression maybe. So let me try and explain. So kind of start from scratch. So suppose we have a groupoid. So let me suppose X is a groupoid. Source. The objects of X are like sets with simply transitive action of this. So the morphism is like an isomorphism. So it's like an isomorphism that commutes with this disadvantage. So suppose we have an involution, so let me call this sense. And the morphism to this inverse transpose. Then the dual of this T that we have the dual of T. Okay, I am genuinely having trouble looking for my cursor. No? So the dual of T can be identified with the as a set. Dual Z1 action by so this is the original action. Z1. So Z bar. So then this so this is equivalent space. Right. And now we have a couple of isomorphism classes. So that's where the type P and type N comes from. So type N and type P. So these are sources. Complex conjugation data as a map to torsion. Cosmos. Complex conjugation. Right, so that was the mini digression. So, okay, so we are not done with this theorem yet. So, again, and find. Oh no, it's at the moment I don't remember of a way I could change the person. We have now this. So here's the other part. I mean, so that was the theorem. Now, so this is just an notation. So the subspace. So this was our space of continuous invertible topological field theories with reflection structure. Right. Invariant continuous topological field theories with type B. So the way we define type P. Sorry. Yeah, type P. Let me make sure. Yeah, so type P. So the subspace of satisfying the conditions of the above theorem. So there is homotopy equivalent to space. Right. So corollary would be I think I should find it. Yeah, okay. Corollary is so there exists a bijection in the isomorphism classes of of course, n-dimensional topological field theories with symmetry, located reflection structure, and partition function of type B and so on. So, okay, so now we have moved. So now we have moved to the next section of the talk. So for the second part, so now I'll talk about positivity and extended invertible topological field theories. So first I'll be talking about some splitting results that will be useful in our main theorem of interest. Right. So positivity in extended invertible topological field theories. That So the splitting of our interest rate comes from the following reserve. There exists inclusion of group extensions of this. So we had seen the way we had extended symmetric group in the previous talk, using a lot of things that I've kind of built up on. Right. So now the middle vertical homomorphism. So from the middle one, there's this one. So this induces the following now. Maybe I can do something by increasing the thickness a bit. Okay, I think we can work with this. Great. Cool. So this middle vertical one, so this reduce here. This induces right from this middle vertical map. And so that kind of gives us a factorization of the projection. We get the following factorization. Projection from this reduced map. So from this actually, so we get a sequence of equivariant maps which will be so this factor is a smash product of the identity map of 1 minus sigma with the defining inclusion of this into this. So that's the idea. So now from the stable form of this splitting, we can have this machine. Very nice. Spectrum. Can now take so this just follows. So you just take the coordinate and goes to infinity of the star. There's the idea. So okay, so now we can talk about positivity. So first, I guess so now we'll first talk about spaces of theories. That's problem. Whoops. Okay. Spaces of theories. So right, so this N that we've been seeing, so as was the plan for all the talks, so I'm not getting into physics of all. So I'm only interested in the homotopy, stable homotopy theoretical tools that we are using in order to understand extended topological invertible topological field theory. So this n is actually the space-time dimension. So let me just mention this space-time dimension. So these are the two invariants that will have this Wick-rotated. So the way, so the thing that we are interested in, like having homotopy type of the deformation classes of invertible topological field theories, which are reflection positive and symmetrical features. So we have two invariants in that classification, one being the space-time dimension and the Wick-rotated dimension. Right? So, great. And then let's fix some integer k. So now suppose G is a label with a homomorphism. So remember the way. So now, okay, so now we are in position. Oh, this is so confusing. So we get a form spectra. Right. So the space of continuous invertible K truncated. So we generally don't mention this K in the notation. One-dimensional topology field theory of symmetry type as this would be a notation. So this is the same. So we just don't write double switch. So how does this category look like? So the point is like so it is a k-dimensional field theory that associates to I don't know, closed L manifold, but L is less than equal to 10. Let me write this down. So the objects of this category are associate to a closed, say, dash manifold. Oops. Okay, I realize that I don't think I've got visual line, super lines or anything before, so trying to get a bit of a digression. So lines, so when I say a line, it is just a one-dimensional vector space, right? So in an n-dimensional invertible field theory, so the vector space attached to any n-1 dimensional manifold is a line. And then this is so that cannot, sorry. So this is our category of super. So we have like we see that we have different versions of these continuous invertible theories with analogous definitions with the discrete versions. So again, it's fixed. Okay, so what is oops and okay. Starting with the first one. First phase of continuous invertible K truncated dimensional standard topological field theories. Symmetry well is so this would make a lot. Let's see all this notation that we have. Where this may not be the antecedent, but it's the stage. So find it. So there's the spectrum of higher Hermitian superlines, right? So that's the way. Or so I think that's what you call it. Then the space of continuous invertible K truncated and dimensional positive definite. Positive definite QFTs, theorems, and symmetry again, this is universe. Right. So here, this is as a spectrum, higher positive definite Hermitian superlines. Think about this. So now, right. So we have a map. So by composing with this map, so composing with composing with this map, get a map. Right. So now, okay. So we did everything pretty generally. So now assume the symmetry type. So that was what just assume the symmetry type is now. So now the way we defined with reflection structures of really called so now we'll compose this now, composing with the first map of the star again. So the star that we had, I think I had found it. But this, so composing with the first map, we'll have a map between. So we'll have a map. Get a map. Composing with the first. So what does this mean? So this means that right. So this means that the value of a theory with reflection structure on a closed manifold of dimension. I'll write this down. Which means the value of theory reflection structure on a closed manifold of dimension. So Hermitian super. lot of functions that we have. So recall that we have this row map. So now we're going to find for the space of n-dimensional invertible topological field. There it is. Let me write it in this. Space of n-dimensional invertible topological fields with symmetric type. Right. So just a notational remark. So for these, for these spaces that we're defining. So for the discrete spaces, okay, I'll just say this. For the discrete spaces, the discrete versions, we're just adding a delta. So something something of something like this, for the discrete version. Something like this. Ready? Right. So what we are interested in, as we've said from the beginning, invertible reflection positive theories. So now from this map that we had, right? So this one that we saw. So from this, saw that an invertible theory with reflection structure. So it has values on closed manifolds of dimension less than or equal to 1 minus 1 that are higher emission superlights. We saw. So now we are interested in imposing the positivity condition. Right? So again, there are things that I will be defining. So again, we fix n greater than 0 and symmetry. So, oops. This means the discrete case of n-dimensional discrete invertible reflection positive topological field theories for symmetry. It's where so the following diagram shows so how do we pull back? Diagram, yeah.